This is Ozwin D'Souza from the Department of Electrical and Electronics Engineering. I'll be taking up the course called Analog Electronic Circuits. So this is meant for third semester electrical branch. The course code is 18E34. So basically this course is interdisciplinary in nature, in the sense along with electrical students, electronics, telecommunication, information science, computer science, all the branches of students will be studying this particular course. Okay, so whatever content I'm going to present, that is with respect to electrical syllabus. All right, fine. So the syllabus is consisting of totally 5 modules, and each module takes about 10 hours to complete. So basically it's a 50 hours course. So in today's session, let me consider first module. Module 1 is consisting of 2 parts. The first part being diode circuits and the second part being transistor basics. So first let us look at module 1A, diode circuits. Now first of all, what we have to understand first is that this is an analog electronic circuits course. So in this particular course, we deal with the continuous signals. All right. So whatever we are going to study in this particular course is based on the basis of continuous signals. So the exciting function is basically continuous in nature. All right. So in diode circuits, the major topics are 2, clippers and clampers. Okay. So to some extent, we all have studied clippers. So clippers are nothing but wave shaping circuits. For example, you can think of half wave rectifier. So in case of half wave rectifier, what happens is that the rectifier will allow the positive half cycle of the input to flow through the diode. On the other hand, the rectifier will block the negative half cycle of the input waveform. So basically, half wave rectifier, it removes the negative half cycle of the input waveform. So clipper is an example for, half wave rectifier is an example for clipper. On the other hand, if we look at clampers, so in case of clampers, the appearance of the signal is not disturbed or changed. If you give a sinusoidal signal, the output remains sinusoidal. On the other hand, if you give a triangular signal, the output remains triangular. So it will not alter the shape of the signal. Instead, it pushes the output either onto the positive DC level or onto the negative DC level. So that means to say, the DC level of the output waveform could be plus DC or minus DC. Okay. So basically, a clamper is a circuit which adds DC level to the incoming waveform. So this being the brief introduction about module 1A, I think now we can get into the exact details of module 1A. Okay. So let's start with clippers. So prerequisite for analog electronic circuits is basic electronics. So basic electronics, you will be studying in either semester 1 or semester 2. Okay. Still, let me make some effort to recall some of the important concepts which you have already learned in basic electronics. Okay. The first and foremost important concept to understand clipper circuit is nothing but the diode equivalent circuits. So we all have seen the diode characteristics, right? So this being the voltage applied across the diode, and this being the current flow through the diode, and typical VI characteristics. Typical VI characteristics of a PN junction diode appears something like this, right? And during reverse bias condition, something of this kind is going to appear in the diode characteristics. Now, diode is basically a semiconductor material. So, to a semiconductor material, we cannot apply Ohm's law. But while doing circuit analysis, we predominantly use Ohm's law, Kirchhoff's laws, and Kirchhoff's voltage law, Kirchhoff's current law, etc. So, firstly, what we have to do is we'll have to obtain a linear model for the diode. So, to obtain linear model of the diode, what we do is we look into the linear region of the diode. So from the p-n junction characteristics, it is observed that once the external voltage overcomes Vk, so Vk is called as the barrier potential, or it can also be called as the threshold voltage of the semiconductor diode. So Vk value is 0.34 for a germanium diode, 0.7 volt is for a silicon diode, and 1.2 volts for a diode made up of gallium arsenide as the semiconductor material. So once the external voltage overcomes the barrier potential, we observe a ready conduction in the diode. So once the diode gets into conduction, the diode starts to behave like a conductor. So the response of voltage and current is linear. So once the diode gets into a conduction, the current rises linearly with the increment in voltage. So we will be considering this particular region for obtaining the linear model of the diode. So this region, we can call it as linear region. You can also call it as ohmic region. Ohmic region. Okay. So from this characteristics, you can obtain an approximate characteristic. In the sense, we are going to discard the transition zone as well as the non-conducting zone, and we are going to extrapolate this linear line such that the line touches the x-axis. So something of this kind, you will get it. So what we have done is we have discarded the transition zone area, and this being I and this being V. Okay. So this is called as piecewise linear model or first approximation. Okay. And the slope of this straight line, say delta y, delta x. So m is equal to delta y by delta x basically gives reciprocal of the dynamic resistance of the diode. Okay. So this particular model is called as first approximation. All right. And this is the threshold voltage. So based on this characteristics, the equivalent circuit of the diode can be drawn something like this. So let's consider an ideal diode. Okay. Followed by the barrier potential. So we all know that the barrier potential opposes the ready conduction of the diode, and that's the reason the barrier potential is placed with this polarity sense. So the positive terminal of barrier potential is connected to cathode terminal of the diode. So that will make sure that the barrier potential keeps the diode in off state. Okay. Followed by the barrier potential, let us try to include this linear line into our model. So this linear line can be represented with the diode dynamic resistance RD. So you can place a series resistance RD in series with the diode model. So this is your first approximation. Okay. Now this resistance RD is quite small. So generally RD for a low power semiconductor diode varies somewhere from 2 ohms to 4 ohm. And when we deal with a very small current value, so the effect of RD becomes insignificant, and that's the reason you can neglect RD for most of the analog electronic circuit analysis. So if we neglect RD, what we get is second approximation. So in second approximation, the RD effect is neglected. So the resultant equivalent circuit of the diode is obtained something like this. So this is your ideal diode, anode, cathode terminal. In short, let us consider it as ID, and this will be in series with the barrier potential plus minus Vk. Okay. So whenever you encounter a practical diode of this kind. So this is your practical diode, which is made up of silicon. So what you can do is you can replace this practical diode with the second approximation circuit. So in the second approximation, what we do is we're going to replace the practical diode with an ideal diode in series with the barrier potential. Since we are talking about silicon diode, so for silicon diode, we are going to place Vk as 0.7 volt. So this particular model is discussed throughout module 1A. So whatever clippers, clampers we are going to discuss, it is based on the second approximation. So now let us take up the clipper definition. So clipper is a wave shaping circuit that shapes the incoming signal at the desired level. If you talk about a bidirectional signal, say for example, the incoming signal is sinusoidal in nature. So this is your input signal, Vi versus time. So that incoming signal can be shaped at a desired value. So output signal can be shaped something like, so blue is my output signal. So what we have done is that using some clipper circuit, okay, so this is your clipper, and to the clipper the input we have given as Vi and the output we are getting as V0. So let us not worry. Let us consider this clipper circuit as a black box circuit. Let us not worry about the internal components of the black box. Okay, so you give a bidirectional sinusoidal input and you get a bidirectional signal whose peaks have been trimmed or peaks have been sliced. So for the same reason, the clippers are also called as the slicing circuits. So using clipper, one can slice the positive half of the input waveform or the negative half of the input waveform, or both the halves can be sliced or clipped. So accordingly, you have different types of clippers. The clipper which clips the positive half of the input waveform is called as a positive clipper. On the other hand, the clipper which clips the negative half of the input waveform is called as a negative clipper. And if a clipper clips the positive half as well as the negative half of the waveform, then you can call it as a bidirectional clipper. So let's start with a simple clipper such as series clipper. Okay, so let's start with a simple circuit and slowly let us raise the complexity. So series clipper. Now, series clipper is a clipper in which the diode and the load resistor comes in series. For example, half wave rectifier circuit, in short HWR, half wave rectifier. And this is the load resistance, sinusoidal input Vi, and across the load resistor, let us measure the output V0. And let's fix the polarity something like this. Okay. So over here, let me assume ideal diode. ID stands for ideal diode. So this is an example for a series clipper. As you can clearly observe that the diode and the load resistor are traced in series manner, and that's the reason the name is given as series clipper. Likewise, you also have parallel clipper. Sometime later, let us understand the working of parallel clipper. Okay. So now let us look at the working of this clipper circuit. So in case of clipper working, all what you have to do is you have to talk about the circuit behavior for a complete input cycle. That means to say, you talk about the working of the circuit for positive half of the input and the negative half cycle of the input. So the entire working is broken into two parts. Okay, positive half cycle working and negative half cycle working. Negative half cycle working. In the sense, what happens when you consider positive half cycle of the input waveform, and what happens when you consider negative half cycle of the input waveform. Okay, so let's begin with positive half cycle. So let us write during positive half cycle. So during positive half cycle, what we do is we try to give or assign the polarity for the source. So when you talk about positive half cycle, what we do is we consider the upper terminal of sinusoidal source with positive sign and the lower terminal with negative sign. Okay, by which we simply mean that the upper terminal is at higher potential and the lower terminal is at lower potential. Okay. Okay. So we have assigned the polarity. Now let us see what happens to diode conduction. So as you can clearly observe that during the positive half cycle of the input, the anode terminal of the diode is getting connected to the positive terminal of the source. So whenever the anode is connected to positive terminal of the source, we say diode is in conducting state. So when the diode gets into conducting mode or conduction state, what we can do is we can replace the diode symbol with a short circuit equivalent. Okay. Conduction means it is kind of short circuit, and open circuit means it is kind of open circuit. So we'll replace the diode with a short circuit equivalent. Okay. And when the circuit is closed, obviously there will be a flow of current, and this current produces a voltage across the load. So V0 is basically I into RL. So for the positive half cycle, the diode is going to get conduct, and due to which there will be a flow of current, and hence the output voltage exists. Okay. So we'll plot the waveform sometime later. Now let us consider the negative half cycle. So during negative half cycle, what happens? So during negative half cycle, all what you have to do is you will have to reverse the polarity of the source, in the sense, now the upper terminal of the source is given with negative sign and the lower terminal is given with positive sign. Okay, I'll retain the diode symbol as it is. And then let us connect the load. And this is how we will be measuring our voltage. Okay. And this is your anode terminal of the diode. Okay. As you can see in the negative half cycle, that the anode terminal is getting connected to negative terminal of the source. So whenever the anode is connected to negative terminal of the source, we say diode is reverse biased. When the diode is reverse biased, the diode symbol can be replaced with open circuit equivalent. Okay. So open circuit equivalent as in we will open the terminals of the diode. So there is no conduction, so current is 0. So obviously you will have to replace the diode symbol. So in this case, the current is 0. Okay, because there is open circuit. So when the current is 0, obviously the voltage becomes I into RL, or 0 into RL is equal to 0 volts. So what is happening is within the circuit that during negative half cycle you are getting the output voltage as 0. So this particular clipping circuit allows a positive half cycle of the input to appear across the output, and it blocks the negative half cycle of the input. So finally we can draw the waveforms. So this is your input waveform, and just below the input waveform you can plot the output waveform. So this is the maximum value of the input Vm, and this is the maximum value of the input in the negative direction. Okay. So for the positive half cycle, the diode conducts and therefore the voltage is available across the load resistor, and the maximum value of voltage will be Vm. And during negative half cycle of the input, the diode gets into reverse biasing mode, hence the diode stops conducting, and therefore the voltage across the load becomes 0. So this is the waveform of the half wave rectifier circuit. Along with the waveforms, you will also have to plot something known as transfer characteristics. So transfer characteristics, in simple terms, it is nothing but the plot of input voltage versus output voltage. Okay. So plus Vi signifies the positive half cycle of the input. The minus Vi signifies the negative half cycle of the input. Similarly, plus V0 is the positive part of the output, and minus V0 is basically the negative part of the output. Okay. So in simple terms, you can draw the transfer characteristics just by looking at the input and output waveform. So input is sinusoidal in nature and output is also sinusoidal in nature for the positive half cycle. On the other hand, for the negative half cycle, you had seen that for the negative half cycle of the input, the output was 0. So that means to say, as the input starts increasing, the output is also increasing in nature. So when the input attains plus Vm status, the output was also at plus Vm. So basically you will get a straight line. So for an AC output, the transfer characteristic is basically a straight line inclined at an angle 45 degree. So this is for AC signal. Okay. On the other hand, in the input-output waveform, you had seen that for the negative half cycle of the input, the output was 0. That means to say, whatever may be the input value, okay, at the max, the input can attain minus Vm in the negative direction. The output stayed at 0 volt level. So you can call it as DC value of 0 volts. So this is the transfer characteristics of half wave rectifier. Okay. Now let us examine the second circuit, in which we'll change the diode orientation, and let's see how the output is going to change. So in the second example, all what we are doing is the orientation change of the diode. Okay. So let's place the diode in this manner. This is RL and this is V0 and this is Vi and this is your diode. I'm considering ideal diode, and this side is cathode and the other side is anode. Alright, so let's get into the analysis part. Analysis. So once again, the analysis is broken into two parts: what happens during positive half cycle and what happens during negative half cycle. So let us first consider positive half cycle. So during positive half cycle. Okay. So during positive half cycle, what you have to do is you have to assign the polarity. Correct. So let's assign the polarity. So how do we assign the polarity? Upper side positive and the lower side negative. Okay. And we'll place the diode in as it is condition. This is the load resistor RL. Okay. And this is the cathode, and this terminal is the anode terminal. As you can clearly observe that the cathode terminal is getting connected to the positive terminal of the source. So whenever the cathode is connected to positive terminal of the source, we say that diode is reverse biased. So diode is reverse biased. Let's say in short RB. RB stands for reverse biased, and due to which, diode behaves like an open circuit element. Open circuit element. So what do you mean by open circuit element? It is something like as though this diode is not present at all. Okay. So we'll just remove off the diode. And that's your open circuit. So during open circuit, there won't be any current flow, hence you can write I is equal to 0 amperes. So since there is no current, so obviously there will be 0 voltage. So V0 is basically current flow through the load resistor RL, right? So that is I into RL. So V0 is current flow through the resistor RL into the resistor. So that's 0 volt. So for the entire positive half cycle, the output stays at 0 volt level. Okay, so that is the circuit status during positive half cycle. So now let's investigate the negative half cycle. So let's write during negative half cycle. Okay, so let us redraw the circuit. And how do you accommodate the negative half cycle? By flipping the source polarity. So this time let's take upper side negative and lower side positive, and the diode is placed in its position, followed by the load resistor RL. Okay. Now, during negative half cycle, as you can clearly observe, that cathode terminal of the diode is getting connected to the negative terminal of the source, and you can say that diode is forward biased. So in short, FWD forward biased. Okay. So whenever the diode is forward biased, you can replace the diode symbol with the short circuit equivalent. So diode is replaced with short circuit equivalent. So this is the cathode and this is the anode. Okay, since I have changed the polarity, I am going to assign the current direction in line with the source polarity, and this is how the current is going to flow. So current flows in a closed circuit. So V naught going to be I into RL. So you can say that during negative half cycle there exists a voltage. Okay, so you can apply KVL. So apply KVL in anti-clockwise direction. Okay, let's apply KVL in the anti-clockwise direction. So minus to plus, it is Vi, and look at the output polarity, again minus to plus, so plus V naught is equal to 0, right? There are only two voltages, the input voltage and the output voltage, or the output voltage V naught is equal to minus Vi. Okay. This is a pretty interesting equation in the sense you can observe the negative sign here, right? So this negative sign simply indicates that the output occurs in the negative direction. Okay, so the negative sign simply indicates that the output occurs in the negative direction. Okay, so now let us plot the waveform. So this is your input plus Vm, minus Vm. So just below the input you plot the output. Carefully place the transition points. So this is the duration of the positive half cycle, and this is the duration of the negative half cycle. So you'll have to roll back to your circuit analysis. Okay, and we had observed that for the positive half cycle, the diode was in off state, and due to which there was no output. So for the entire positive half cycle of the input, the output will stay at 0 volt level. On the other hand, when we look at the analysis of the circuit during negative half cycle of the input, we had obtained output V0 as minus Vi. So minus Vi as in negative half cycle of the output. So output is nothing but negative half cycle of the input. So this is how you get the output. Minus Vi. So when the input attains minus Vm, the output will also attain minus Vm. And side by side you can also plot the transfer characteristics. Okay, so transfer characteristics is a plot of input voltage versus output voltage. Okay, so let's say this is the maximum limit of input voltage, and minus Vm going to be the maximum limit of the negative half cycle, right? So for the negative half cycle of the input, the output is 0. So 0 as in you need to overlap the positive x-axis. Okay, and you can just write 0 volt level here. Okay, on the other hand, for the negative half of the input, you are getting an inverted output, right? So when your input is 0, output is 0. When your input attains minus Vm value, the output will also attain minus Vm value. So when your input attains minus Vm value, the output also attains minus Vm value. So which is nothing but a straight line. Okay, and the angle is 45 degree. Okay, because you will get a perfect square, and the diagonal will have an inclination angle of 45 degree. So this is the transfer characteristics of positive clipper. So this is an example of positive series clipper. Okay. So the diode and load resistors were traced in the series manner, hence it is a series clipper. And with this circuit, you are able to clip the positive half cycle of the input, hence it is called as positive clipper. So in today's session, we have looked at the two types of series clippers, positive series clipper and negative series clipper. So in the next class, let's look at the parallel clippers, and let us also consider the practical diode model. So practical diode as in you will have to refer to second approximation equivalent circuit. Thank you.